Okay, so today we're going to start a new unit on rotational motion. Who remembers what we did with the bicycle wheel earlier in the year? Anybody? Yeah? Yeah? You remember what we did? Spun it and it stood up. Yeah, in fact we could do that again in a minute. I'll show that in a minute. What I've got here arrayed on the table is a whole bunch of things relating to rotational motion. Now that you've gone through basic mechanics, we can get to some of the more interesting stuff, because the interesting stuff is the stuff that you don't expect to happen, right? Things like a bicycle wheel standing up by itself. Actually, James, could you go get me that bicycle wheel, please? Just be careful not to set off the yeah, that one. Thank you. Okay. All right. So what we're gonna do here is just do a recreation of the demo I did earlier in the year. And obviously, if I hold this by a string, it does nothing, right? But if what I do is set it going like this and hold it by the string, now it stands up, right? Now, this is something that is very helpful for anyone who rides a bicycle or a motorbike. You can see that if your wheels are spinning, you've actually got something that's helping you stay afloat, right? That's why if you're a learner on a bicycle, you don't want to go very fast. It's actually worse for you than if you do go fast, right? Because if you're going fast, the wheels are turning, they do not want to change their orientation. Now I could do this, right? And now it won't want to change the other way. It doesn't matter if it's going straight up or straight down. Whatever is happening in terms of the rotation, it does not want to change. This is actually an example of the conservation of what is called angular momentum. You've already come across linear momentum, right? So in order to understand something like this, or Sujit, could you take a stool out the front there? What we're going to do, I'm going to get Sujit to come over here and sit down on this. All right, I want everyone to come over. I want you to sit back on it, right? And what you're going to be doing is you're going to be having your feet up in the air. I mean, you're just going to hold them, right? Now what I'm going to do, what I want you to do is hold on to both of those handles, and now I'm going to make this thing go. And what I want you to do is try to twist it in either that direction or that direction once it's going. Okay? Okay, so let's start that again, because I think that you weren't prepared for the pull. Okay, so we'll just stick this in here again. And this time, can someone hold Sujit's shoulders so that he's not pulled off? Right, he's going to be pulled this way. You ready? All right. So, are you making yourself move like that? You're not. You're not, are you? No. So, again, you can see there's actually some sort of force that's making him move, right? Because changes in motion only come from the application of a force. All right, let's take this again. Now, I want somebody who has a few muscles. You're Christian. You're good because you're a golf pro, right? Okay. So Christian, come over here. Now, what I want you to do is sit back on this, right? So you're sort of balanced on it because you're going to lift up your legs, right? And your legs are not going to be touching anything. All right? Now, what I want you to do is hold this straight out, right? And I'm going to rotate you. And what I want you to do, keep your legs off the stool. What I want you to do is, once I've got you going, I want you to pull that in towards your chest. No. You pulled it in and pushed it out. Why did you do that? Did you get afraid of something? Huh? Let's try it again. What happened?
Faster.
You move faster, push it out.
Make you afraid.
Well, it's very disconcerting, right? It's very disconcerting to find yourself without any external influence suddenly speeding up, right? In fact, why don't you try, Jason? Well, you know, that's what happens when you diss somebody, right? Okay, so you've got to hold it right out as far as you can. Lean forward. There we go. All right. No, you pulled it in too fast. All right. Just let me get you going first. You ready?
Yep.
Now pull it in. Pull it out. Pull it in. What other thing have you seen that's similar to this? Sorry? A swing, yeah. What do you do in a swing? You pump your legs. Yeah, where else?
Figure skating.
Figure skating. Have you ever noticed how fast those figure skaters go? What do they do when they go into one of those spins? Anyone? Well, they do this, right? And then they do that to slow down. Have you noticed that they always finish by doing this, but when they want to go fast, they go into the turn, they put their arms up, or they do this. What are they doing? What exactly are they doing? What is the change that's happening?
They're making the mass more central.
That's a great answer. They're making the mass more central. That's exactly what they're doing. Rotational motion is really cool because of all the different things that happen. It's a little more interesting than the basic stuff, but we couldn't start learning about this until we got to where we are, right? Till we'd gone through the more basic stuff. Let's have a look at something else. Who plays football? Anyone? You don't play football. Nobody plays football. Who plays soccer? Okay. What do you do? What do you do when you're trying to take a kick on goal that might distract the goalie? Yeah, I mean, to make the goalie think it's going to go one place, but it ends up going another.
I might look one way, but another way.
Yeah, what do you do? Do you do anything with your kick ever?
I don't know. I guess I can curve it.
Oh, you could curve it. All right, how do you go about curving your shot?
You kick it with like the inside of your foot.
So what are you doing when you're curving it?
Like I swing through it like this.
Yeah, I understand that, but what happens to the ball as a result of that kick?
Oh, it has a sideways spin.
It has a sideways spin. Now, I understand that Christian knows all about this because of his wicked slice in golf, right? What are you, a scratch golfer? Almost a scratch golfer. How often do you slice?
I hook it the other way.
Oh, you hook it?
Yeah.
Ah, all right, but that's the same thing, right? What's happening when you hook it? It's spinning the opposite direction, exactly. It's rotating like this, but it's spinning the opposite direction. When you see someone hit a golf ball out, you sometimes see it go straight out on a drive, and then what does it do? It goes up. How is that? It's spinning which direction? Backwards. Then you sometimes also see it hit the green, and what happens? It comes backwards. What has the golfer done to make that happen? What if he wants to stick it? What does he try to do? Less spin, right? It's all about spin. So spin actually affects everything. It even affects railway lines. It even affects railway lines. Who knows what the shape of a train wheel is?
Isn't it like the cups?
Hmm?
Isn't it like the cups?
You think it's like these cups? Okay. It's not like these cups? Like this? Okay. So let's test the theory. What would we hope? Whose bag is this? All right, so I need an assistant up here to come and hold these. Actually, I just need a piece of wood or something. Could you grab me a piece of wood from over there, please, Laurie? Look, near the bandsaw, just that thick piece, that piece there, yep. Okay. And what I want you to do, I'm going to stick these on here, right? And what I want you to do is hold the ends perfectly straight up and down, right? Now I'm going to stick this on here. Now, would you like to be on the train that had wheels that did that? No. Okay, give me the other one. Let's have a look and see. I'm going to put this one on sideways too. Whoa, that's a little bit different, isn't it? Let's try it again. Come up here so you can see, right? We've got two rails, right? These represent the rails. These represent the wheels on either side of the bogie, right? These represent the wheels on either side of the bogie. What I'm going to do is this. No, I would not particularly want to be on that train. It comes off the tracks very easily. Let's try this one. I'll put that one at quite an angle as well. Oh. Now that train I would like to be on, right? Question is, why does that happen? Why does it happen? Why does it happen that way for that one and this not so helpful way for the other one? No. No, actually it's not.
Well, you threw me off then. It's torque.
No.
Okay.
It's something a lot
Center
simpler.
of mass.
No, it's something a lot simpler. You don't really have to think so hard about this. What is happening with this as you go from here to here?
It gets smaller.
What's getting smaller? And therefore, what's happening to the circumference? The circumference is getting smaller, right. So if this thing is put on, could you hold that again, Laurie? If this thing is put on there like that, right, we have a large circumference here, we have a small circumference here. But they're linked, right? They can't move. So what do you know about this side compared to this side, just on the basis of their circumferences when I let them go?
One's bigger.
Yeah, but what's going to happen? Yeah? Exactly. Because they've got to cover the same amount of distance in the same amount of time, right? So the amount of distance around here is different. So if I put this here, that's what's happening, right? It's trying to get back to that balance where both of them are in fact perfectly centered. Right? Where both of them are perfectly centered. Okay, there's another interesting thing that we can do, and I don't know that I can make it work on this because it might be too. I've actually, a couple of my things have gone missing, so it makes life a little difficult. But what I'm going to do is I'm actually going to put this thing on a slight slope. Right, so that you agree that that's uphill, right?
Yes.
Yeah. And now I'm going to stick this down this end. What do you expect to happen?
But
It's going to climb up? How's it going to climb up?
It just is.
Huh?
It is.
Why?
Good momentum.
No. Sorry.
Because it wants a smaller radius. Or a large, yeah, smaller.
No, we need to think about something just slightly more complicated that we've covered before in order to understand why this is going to do what you're predicting. Let's see if it works first. Laurie, could you hold that again? Because it may not work with this thing. No, it's not going to work. I did have... Ah, there we go. All right. So notice how it stopped and then it moved up further. I actually have a better one of these, and it would have gone all the way to the end. What's happening is the center of mass is getting lower, even though the thing itself is getting higher. Because notice what I did was I stuck these out like that, right? If I put them out even further, I might actually be able to get it going. No. I'm sure that tape is not helping. Let me see if I can get it out a little further still. So put yours in a little bit closer. There we go. Closer. Okay. Okay. So I'm not giving it much of a push. I think the thing is that this is not balanced. Right? It's got more weight of masking tape on one side than it does on the other, and so consequently it doesn't want to roll. But it did in fact climb that hill, right? And the reason is because it's actually going down. The center of mass of this object is actually going lower, even though it appears to be going uphill. So there's lots of interesting stuff that goes on. This thing here you've seen before as well, right? It's a top, and tops like this, it's doing what's called precessing at the moment. Tops are the basis for gyroscopes, right? Just like that wheel, right? Didn't want to move. So if you put something that's spinning like this inside a cage, and inside the cage you've got these very low friction bearings, so that if you move, this thing can actually move within the cage, you can make what's called a gyroscope. And that's used for navigation, right? Because if you take the signals, right, if you have like a resistor in the arms, you can measure how much the resistance change, and you can say, oh, that means that much angle went by. We needed gyroscopes for the moonshot in the 60s. Didn't have GPS or things like that, and I'm not sure that would have helped. I mean, there was one case where one of the spaceships was actually tumbling, right? And they needed to find out how it was tumbling. And what gave them information were the gyroscopes. Intercontinental ballistic missiles use what's called inertial guidance systems, gyroscopes, because this is a type of inertia that we're talking about now. But rather than talking about the inertia of a single point mass, which is what we've always talked about in this class, now we're going to take into account the geometry, right? The geometry of this. Now I did have a demonstration, I don't know whether I showed it to you, of two rings going down a plank. Did I show you that? No. One was, they both had exactly the same mass. Unfortunately I can't find it. It has disappeared somewhere. They both had the same mass, but one of them was a metal ring, right, that was had all its mass concentrated in the outside of the ring, and the other one was made of a solid block of wood. Remember, they both had the same mass, the same dimension, same mass, right? Everything else was the same except the distribution of the mass within the object. I then put them on a sloped ramp like this and let them go. What do you think happened when I did that? Which one? The wood one got to the bottom faster. Does everyone agree with? Okay, and why do you think that is? That in fact is absolutely true. So what we actually start talking about when we're looking at rotational motion is a thing called the moment of inertia, right? So that becomes, the moment of inertia becomes our equivalent of mass in a linear system, right? So we take the moment of inertia and we multiply it by the angular velocity, right? Because if we use the angular velocity, we've taken into account the fact that all the particles are actually moving through the same angle in the same amount of time. If we look over here, we're going to now get back to more basics. So if you come over here, please. So what we have here is just a table with some numbers on it. So this is 0 degrees, or 2 pi radians, 360 degrees, pi over 2, 90 degrees, and these rings show radii of 10, 20, 30, and no, diameters of 10, 20, 30, and 40 centimeters. And then I've got these posts here. I'm now going to increase the current. Okay. So this is now rotating. This pin here is the same as, let me turn it off. This pin here is on the same place, right? What can you tell me about these two different pins in terms of velocities?
The outside one has a higher velocity.
What sort of velocity would you call it? I understand the greater one, but you might use a word beginning with T. Sorry? Yeah, a greater tangential velocity. That is, at any particular instant, right, the tangent to that radius, at any particular instance, that one has a greater tangential velocity than this one here, right? What else can you tell me? What else are those things doing?
Rotating.
They're rotating, right? And they're rotating at the same rate. Exactly. And when we say they're rotating at the same rate, we say the amount of angle per unit time, is the same for both of them. It turns out that there's a nice relationship between this velocity, the tangential velocity, and how far it is from the center. In fact, all you need to do if you're working in radians is to in fact multiply the angular velocity by the radius and you'll get the tangential velocity. And that just comes from L equals R theta. Remember that? L equals R theta for an arc length, right? So if you've got if you're looking for a change in that distance it's traveled, it's going to be the radius times the change in the angle, right? You divide that by delta t, you've got delta L over delta t, which is the tangential velocity, and then you've got R times delta omega on delta t, where delta omega on delta t, sorry, delta theta on delta t is the angular velocity. All right.